Hello community, welcome to DSPy 5, where we look at the implementation of a RAG system with a graph neural network. Let's go here. You remember in my last video, I showed you here in a DSPy module where we had the class of the multi-hop question answering. So we have a complex question and we have then simple question 1, simple question 2, and simple question 3. Decomposing the complex question, I told you, let's do a graph. And then for each query, we retrieve 3 text documents, 3 text passages, 3 text paragraph, whatever you want, either from a vector store, from a SQL, from a keyword, whatever you have. And now I started to rebuild this structure with a graph neural network. Houston, we have a problem! Houston! So what happened? I took a query and I extracted 5 text passages. 5 text passages, and I was sure in one of those was the answer to my query. But my graph, my newly constructed graph neural network told me, hey, there's no significant correlation in my subgraph. So none of these 5 are answering your query. And I said, okay, I increased to 8. And my graph network told me there is no significant correlation in this subgraph of 8 elements. Your query is not answered by any of these 8 elements. And I said, let's increase to 10 retrieved RAG elements. And my subgraph, a little bit annoying, I have to tell you, it was a little bit annoying, came back and said, hey buddy, no significant correlation in any of this. This was the time that I started to focus on the information retrieval. Yes, I encountered, this is me here, a roadblock. But you know what is the beauty of a roadblock? It crystallizes the problem. So we can now focus on the first problem. So what I did, I checked my retrieval model. I said, okay, you know, the retrieval model, the other thing at the other side of the intelligent DSPy RAG pipeline. And I used Colbert as my information retriever here. Colbert version 2. It is really fast. Scalable, BERT-based, attention-focused search over a large context in milliseconds. It works great. Stanford, Future Data, Colbert, GitHub. Great. And I looked at this and it says, yeah, beautiful. So let's go there. And I found here, hey, latest announcement. As of end of January 24, Ragatouille library is the easiest way to use Colbert, maybe the latest version. So I said, I go to the latest Ragatouille. I went there. Please notice that these notebooks do not run on Google Colab and do not run on Windows. So, you know, current limitation. And I had a look at this. I said, yes, I learned from their Python notebooks, the demonstration. And notebook number 4, you have this here in the bottom right corner here, if you want to go there yourself. You have here Ragatouille. You have here pre-trained Colbert information retrieval, Colbert version 2. Beautiful. So I take this, I have here my sentence transformer, I train it here on my data set, I go to the classical whatever. In the official notebook, let's stick with this. They say, okay, now we go to the Wikipedia page, and from Wikipedia, we extract documents for 3 topics. And the second topic was Studio Ghibli. I don't know what it is. Never mind. They said, hey, for a processor, we have a chunk size of 200 tokens. Beautiful. So we built our index. Great. And then in the official notebook here for Ragatouille, so for Colbert, the question was easy. What's Ghibli's famous policy? And they say here, an existing pipeline, the query, extract 20 relevant text segments from all of Wikipedia that you can find. And you know, information retriever now in February 2024, we do not go with dense retriever, but we go with scalable, attention-like scoring for a multi-vector embedding. Reason, real fast, lightning fast. You remember in the classical SBERT, we had to do a dot product between each and single vector and each and every other vector. Very precise, but very slow. This here, with Colbert, they preserve here the retrieval precision of the BERT attention mechanism. So they just aggregate here the sum of the maxim for the query token to the document token. Thereby, they only touch here with their calculation less than 1% of the data. And the other 99% of the data they can judge as not really contributing them. So they are focusing on less than 1% of their data, of their vector calculations. They're lightning fast, real fast. Beautiful. So you see here, we extracted here 20 text, one chunk, another chunk, and you get it. And so after 20, now in the official RAG notebook, they told us, hey, now we can see that the result we are looking for is explained here. The document paragraph that we were looking for, it's ranked 14th most relevant result. And now I understood, because in my pipelines, I had 9 or 12. So I retrieved 9 to 12 documents. Because I thought within the 12 documents, I'm sure there's one that has the answer to my query. But now, even if in the official documentation, they say, hey, this is 14. And they say, hey, in a real RAG pipeline, this is often well outside of the context you would give to your LLM. And this is not just because the context length finds their limit. But I was not aware that you have to to retrieve such a huge amount of data. And I said, okay, so if I now take not a simple document query from the Wikipedia pages, what if I take here a scientific publication on a science domain knowledge and a brand new publication on a complete new topic with new logical reasoning paths? What would happen then if I do hear this? And then I find out here my relevant retrieved astrophysics text document, text passage was 42nd text paragraph that was retrieved by my RAG system. And now I got an idea why my RAG did not work on brand new science topics. Because if we slice up our document in tiny, tiny slices, the slices is about 100 tokens, 200 tokens, 256 tokens, whatever you choose. If you have brand new knowledge in a vector embedding, in a vector store where you have your query vector, and you have a lot of knowledge of the information retrieval that is established knowledge, and now you go to some new knowledge, some new research results. Let's say this yellow dot here. And it is the 42nd most relevant text retrieval passage that you have. You see it is not at all close to the query vector. So here we have to have either an angle, a cosine similarity operation, or we search here in a local environment in our vector store, in our vector space that is huge and integrates all of non-relevant information. Because this here is at the fringe a weak signal. And I try to train my Colbert here on this particular single event. But you know what? My AI system told me, hey buddy, you know that I'm a pattern recognition system here in BASIC. You have to train me on hundreds and thousands and millions of training examples, and then I will statistically find patterns in this. If you give me one single training example that is nowhere else to be found in my normal pre-trained, in my established training, this is such a weak signal, I put it far, far away from me, and therefore the vector embedding, the classical RAG system, the classical vector store will not work. And I have to look at the AI system and say, hey, buddy, I understand you. Because new semantic correlations are not available within the retrieval model, since this is new research. But please note that this is specific to the knowledge body. This is specific to your knowledge domain. If all of this is astrophysics and you train it on astrophysics, and you have a new research, it will be here. But if you are a student and you learn astrophysics, this is enough for you because you have to learn this piece of information and this piece of information. So if you are starting brand new in a new domain, you need here the basic knowledge, and then you go out and further away and further away. But you know, if you have science and you see this crack in the science rack, and you look inside of this crack here, and you see here a weak signal, it's not so weak by the way, then you understand the rack system fails on this, and you have to be aware of this. Contrary, if you have, I don't know, US news, where you have politicians, and those politicians every day they say simple things that are bound within one sentence. So politician A says message A, and politician B says message B. And there's no complexity to it. There's no augmentation path. So there's no statement like, hey, analyzing the macroeconomic conditions of the US economy and taking into consideration the financial limitations currently imposed on us by the Feds, I think analyzing here the current, linear regression here of inflation and taking into account new political initiatives, I would come to the conclusion that I would propose ABC. This is not happening. In social media, in the news, you have a headline where the information is all within one sentence. So for the attention span of a goldfish. There, in these circumstances, in this domain, RAG works perfectly. But don't start to go into logical reasoning or building paths. This now has some dramatic consequences because this is an image I showed you in my last video, where you have a multi-hop. So you have a complex query, you have a simple query, simple query, simple query, simple query. And to answer the simple queries, you retrieve 3 text passages. This is not working because we now know that for a general question, at least go with, 40, 50, 100 text passages retrieved. So this question alone should go with this amount of retrieved data, retrieved information, whatever sources you have. And if you have a particular domain, like astrophysics, where you try to find new knowledge, or you upload new scientific publication, or you are in finance and you have a new financial algorithm, or you are in medicine and you want to explore new medical procedures, or you are in biopharmacal or in biomedical research, this will not work for you. You have to, I don't know how many documents to retrieve. So I found that I made a mistake in my parameter of my RAG system. Yeah, by the way, astrophysics, I was asked by one of my viewers, hey, is there a good YouTube channel to explain recent astrophysical knowledge, new research? Absolutely. Go to Dr. Baki. She is amazing. So what I need right now is new insights from Google and from Stanford University. And luckily, when I did my literature search, I found documents both published less than a week ago. You have here Google research published at the end of January 2024, University of California, UC, and the University of Science and Technology in China, coming up with not the RAG, but a corrective RAG system. Brand new, none of your RAG system has this. And Google Research argues here, LLMs, beautiful. And we have this RAG system, they complement the LLM, but they rely heavily on the retrieved document, raising concerns. What happens if the retrieval goes wrong? And they try to find now a solution to exactly what I described to you, And it's amazing that there is a publication out there in the exact moment that I need it. Maybe I'm too late, but never mind. Google Research found a solution. And they said, hey, we have now this corrected reg system where, because we have a considerable portion of text within the retrieved documents by our reg, by our R, that is not essential for the generation. And that should have not been equally referred to and involved in the reg system. Now, we all know that we have then a re-ranking algorithm, and we can do another re-ranking, we can do another run, and then have a different so we can run it so often that sometimes it will bring us statistically the correct answer. But I do not believe that this solution, quotation mark, is the best solution to our reg system. I think our reg system can be even more intelligent, can become better, faster, higher performant. And this is the way to do. So Google, look at this example by Google. It said, hey, I have my query. What is the occupation of a person? And if you have a document that says, hey, this person and he was a politician, beautiful, you know the occupation. If you have a slightly more semantically challenging question, who was the screenwriter of a Batman movie? And you retrieve documents from, I don't know, Wikipedia and says, hey, when this script was rewritten about who is Bruce Wayne's parents, now notice, here we have screenwriter, and here we have script rewritten. And now the reg system decides, hey, this is close enough. This is a text I return to the reg to augment here and provide data for the generation. However, this is wrong. This leads to a complete wrong path, to a complete wrong solution. This should not be included. And Google Research and UC and all the team said, hey, what we do, easy. We have our query, our question. And if it comes in, we have at the input to our reg system, we have an additional gatekeeper, an AI system that acts as a retrieval evaluator. So whatever comes in as input, we have here our AI system and says, hey, I have only one job to check based on my pre-trained and fine-tuning on this knowledge domain where this question is living in, medicine, law, whatever you have. If this piece of text that is retrieved is correct, will provide an answer to my question. Is incorrect, then I just throw it out and start a new web search to Wikipedia or whatever you have defined. Or if I don't know, and I think the I don't know class is quite huge if you do science, because those are simple ways to decide. But I don't know, I think is a little bit challenging. Anyway, so you see here, if it's correct, we do a knowledge refinement, we can filter it. Incorrect, hey, we just do it again, and beautiful. This is C-RAG, this idea. So you have a lightweight, fast to fine-tune, because you have to fine-tune into your knowledge domain, a retrieval evaluator. Yes. Action correct, beautiful. And this retrieval evaluator, Google chooses its own LLM, a T5 large. And I tell you now a secret. If you go for an LLM below 1 billion free trainable parameter, a T5 is the industry workhorse. A T5 is there for you. You can fine-tune the hell out of a T5. This is a beautiful thing. Fast, extreme lightweight, less than 1 billion, and it can solve the task if you have enough fine-tuning. So here, for every question, 10 documents are retrieved. The question is concatenated with each single document as the input, and the evaluator, our T5 LLM, predicts the relevant score for each question document pair individually. Let's say from -1 to 1. Great. If it's incorrect or ambitious, we can try again for Ben. Now, the interesting part is, you know that we don't have RAG. Here in this video, I show you a self-reflective RAG for multi-AI agent and I explain here the self-RAG methodology to you. Now, what Google did is they went from a self-RAG to a self-corrective RAG, so a self-C-RAG. They implemented this not only for the RAG, but for the self-RAG system, which is beautiful. And yeah, they said, hey, we tried also ChatGPT, but ChatGPT underperforms. You can't, for different reasons, another video. So they used this T5, and they said, compared now with the critic model of a self-RAG, the evaluated design here in the C-RAG shows two great advantages. At first, the T5 is with 0.77 billion free-trainable parameter, lightweight, lightning fast, even compared to a Llama 2 that is 10 times as big. And the evaluator is free from any human or LLM annotations. So you see, to go from a self-RAG to a self-C-RAG, maybe I do a specific video on the self-C-RAG performance, but if you look at the figures here, it is impressive. Look at the pink block. You go from RAG to C-RAG and you get here from 40 to 59. And you go from self-RAG to self-C-RAG and you jump from 54.9 to 61.8. But also, if this is just for one particular benchmark sector accuracy, if you go with another data set accuracy, this jump here from RAG to C-RAG from 40 to 75. This is significant, and this shows you how to solve my problem number one. Beautifully. Now, notice that my problem number one is solved. I immediately encountered the next problem. Welcome. Yes, I know. I'm the lucky one. Going back to this document, let me show you the idea. I want that you get a feeling for this. So, we slice up our text. So slice, 100,000 of little text pieces. Beautiful. And now we let's say for the logical, as I as a human, if I read this and you ask me, hey, what is the logical path? What is the logical reasoning happening? I would say, look here, this sentence, here we start, then here we have some additional information, then we go here, we combine it, and then if we look at the graph, we see, there's a nonlinearity, and so the final explanation is here. So you see, I go step by step by step, and I pick up, as a human, the most important facts. But you got it, yeah? This is a DAG, this is a directed acyclic graph because my storyline, you can build here this simply storyline. And you cannot build it, let's say the first storyline was about a galaxy, but the second storyline is about stars, and maybe at the end you can combine them. So you see, two storylines appear for insights into the new astrophysical ideas. But here, if everything is chunked up and you throw everything together in a mixture, like in a vector store, you know what you encounter? You encounter my second problem. For the galaxy reasoning path, I have here everything about that has a semantic similarity close to galaxy of my local environment and beautiful. And as I showed you here, the new scientific information that has not been integrated here in the knowledge corpus, in the traditional knowledge corpus. Even if I fine-tune my Colbert file too, if I do here the fine-tuning, I have only one scientific paper, one data set, one way of logical reasoning that I can present to the AI system. New semantic correlations are not available within the classical retrieval model, even if you fine-tune your Colbert, since this is a new research. So you have to take care about your hyperparameter tuning. Beautiful. And if you have this now with multiple storylines, I have a simple question for you. What was the logical path of arguing that I showed you in the linear text that now in a vector store, the RAG system should find out the most important step-by-step logical argumentation chain of thought elements in my chunked up text and tell me, what is the path from this sentence to this sentence? Or was it this sentence to this sentence? Or this sentence to this sentence? In a vector store, you have no chance of identifying this because you have no graph. The only thing that you have is a distance here from one node to another, from one element to another. And logical augmentations are not encoded in distance here. So you see, if this is the information you're looking for Galaxy, and this is the information you're looking for here for the star, you're not going to find it in a vector store. And this is where I stopped and I encountered my second roadblock. So what to do? What to do? The consequences are quite harsh. In my last video, I showed you, you have the complex question, how do solar panels contribute to environmental sustainability? We make 3 simple queries out of a complex query. Yes, ABC. Now we understand, now applying here to graph analysis for GNN, I understand these 3 simple queries are not the perfect way to combine here to find an answer to this question. This is just one of many possible multi-hop structures. If you want an image, think about this are your big chunks. Now we take paragraphs or even documents. And now you want to go from here, this is your starting ground, and let's say this is here your final causal argument. How do you hop? You hop from here to here to here to here, or you hop from here to here to here to here to here, and yes, to here. What are the nodes? What are the graph? What are the edges? You have no information about this. There's something missing in our RAG system today. Remember, RAG is just a retriever. It is not the general artificial intelligence of a GPT-4. Yes, we can combine it with GPT-4, but this is not a typical case. And now you might say, hey, finally we have some insight from Stanford University. This is the reason why I'm here. Okay. There's a beautiful new paper for ICLR 2024 from 2 days ago from me filming this video. So everything happened in the last week. And I would already missed it because the title, I could not identify the title, Recursive Abstractive Processing for a Tree-Organized Retrieval. But if I see Christopher Manning as the supervisor of this publication, you can be sure I'm going to read this. So, Stanford tells us, RAG system, retrieval-augmented language models, can better adapt, beautiful, but most existing RAGs retrieve only short chunks of text from a retrieve corpus, limiting thereby the holistic understanding of the overall document context. This is exactly what I showed you here in my astrophysical paper with this logical reasoning path that goes over multiple pages. Now we have it here, professional from Stanford, 2 days ago. If you want to imagine this here as an image, please, this is it for you. It starts all with the construction of a Raptor tree. So what we do? We begin with segmenting the retrieval corpus into short text of a length of 100 token, maybe 200 token. But Stanford decided to move the entire sentence to the next chunk rather than cutting mid-sentence. So you can be sure one sentence is in a one text chunk element, maybe 256 tokens. So this preserves the contextual and the semantic coherence of the text within each chunk. Beautiful. So the first problem is solved. The texts are then embedding using here the sentence transformer, an expert system. They use here an optimized one. The chunks and their corresponding expert embeddings form now the leaf node of the new proposed tree structure. Any structure, never mind tree structure. Think about a multi-layer structure. And then, to group similar text chunks, they employ, you would not believe it, a clustering algorithm. Is it as easy as this? Once clustered, the language model is used, it will be GPT-4, to summarize the group text here. And these summarized texts are then re-embedded in the vector space, and the cycle of embedding, clustering, summarization continues and goes on. you end up with a multi-layered representation, and you have now two query methods to explore this: the tree traversal method and the collapsed tree method. This is here the original paper. You have here A or B. Here you have the complete multi-layer structure, and you remember, like in my storyline, you go from this to this to this, and then you know, if you have now a query, those are the elements that you have to retrieve, and only those. And your query and the LLM will generate an answer given here. In these pieces of new text, of new research data, this is important to answer this query. But to find this, they use here the intelligent and the recursive summarization of GPT-4. If you collapse all of this into one layer, you have here the collapsed tree retrieval methodology, where also GPT-4 is challenged here to find exactly the retrieved context, given here a particular structure. I'll show you in a second. But please note, and this is now interesting, the second B methodology of the collapsed tree retrieval is, as Stanford writes, effective for multi-hop questioning. And this multi-hop question is exactly where I started this video. I told you we have the DSPy module with basic multi-hop question. So we have one complex question. GPT-4 divides it in 3 simple questions. And Stanford tells us, hey, for this multi-hop question, collapsed tree retrieval is now the new method to go. None of your RAG system will have this. This is brand new. Filming this video. Okay, so the problem is all the RAG system falls short by focusing only on the short text segments. Now the solution is Raptor with the long tail knowledge, our long augmentation path. Yes, they use GPT-4. They have the money for this. And you can have at least 20% absolute improvement in the accuracy if you use Raptor compared to other RAG systems. Great. Now, for the clustering mechanism, they use here the simplest Gaussian mixture model. Yes, beautiful. But then there's something especially beautiful. You have to see this. UMAP. And you know UMAP, the uniform manifold approximation and projection methodology by, I think, Leland McInnes. Beautiful idea to optimize here the clustering algorithm that happens in a high-dimensional space. And we have to bring it down to reduced dimensionality. So to go from multi-thousand-dimensional vector spaces to computable, fast computable vector spaces for the clustering. But you want to have the information conserved also in the low-dimensional things. And yes, here you have it, June 2021, one of my first videos where I used UMAP here on the SBIRD in a Jupyter Lab here for this exact thing. 2022, I took here the IPCC report with 3,600 pages, and I did here the UMAP clustering. And if you want to have an insight into this, I have here the parametric UMAP, the fast and furious, quick and dirty, or the opposite, if you go with the parametric UMAP methodology, explained for the maximum tuning, everything tuned to the max, every parameter on the top level. This is the video for you. Of course, if you want UMAP explained in 59 seconds to go from here a vector structure to a graph structure to a pure topological interpretation, you are not gonna miss out on this video. And if you think, hey, this is a little bit trivial, can it be a little bit more challenging for me? Yes, welcome. I have here a fuzzy neural network where we code here the fuzzy simplicial complex topology in AI. So UMAP on my channel, I was amazed what I did already in the past. For Ben, I explain here recursive summarization in detail. Ben, take your time. Step 1, step 2, step 3. Great. This recursive summarization allows Raptor here to query information at different levels of detail. Just think about this here. You have here a structure with multiple levels. And on each level, you have a different level of detail. And this Raptor can go and search here everything for your particular query to be able to answer this. If you want to have the process structure, and this is it for you. But now we found a solution to the first problem I encountered. And I would not have encountered my problem with RAG if I would not have applied the graph neural network on this. This showed me that there was no significant correlation by my query and my received text documents. And now I understand I have to go with retrieve text documents, I don't know, maybe up to 200, and then I don't want to do all this re-ranking. I know it's a feature, but I want a RAG system that brings me back exactly what I'm looking for, and not, 99 text passages that are absolute nonsense to this. But okay, never mind. And second problem, this logical reasoning pathway. Please remember, we are talking here at the forefront. This is the retriever that goes to the internet and searches for text that answers maybe your query. So, on the internet, you find a lot of highly specialized, non-informative text. And now our retrieval model is not intelligent enough. Currently, no way to find really the interesting passages. It retrieves a lot of things we do not need. We throw away 99% of it. And we hope, like gold, when we dig for gold, we wash the gold. We're looking for this 1% or maybe even less that maybe is in our retrieved text document. And I think this is not good enough. Yes, I know we can have multiple re-ranking and we go all the system again and we run it till infinity, and maybe we hope statistically there will be somewhere the correct information. But I think we can do better. We can have a better mathematical implementation. But this is just my idea. Doing this graph neural network showed me two problems in RAG I have not been aware of, and I hope with sharing here my insight, I can help you and maybe you encountered here the same problems. So here we are. A short video. RAG, the retriever, is not at all solved. Not at all. And maybe I will introduce here in my program here a graph layer, and maybe simple graph layer as a warning that tells me, hey buddy, RAG, the retrieval, now retrieved 100 text documents, but as a graph I can tell you, none of those 100 documents is relevant for an answer. So you better do it again. So you see something similar like Google Research was doing here with this kind of input evaluator, the T5 system. I think a graph system might be even better suited, but this is now competing systems. But I think open source community, this is beautiful. I'm sure they will take it up and they will find a much better solution where our current RAG system fail, that they will at least give us a warning that it is failing and tell us why it is failing. Or you implement here the RAG system completely with a full implementation of a graph neural network. It is completely up to you, and now I've given you maybe even a second idea. If you want to do research in AI, if you want to do your master in AI, if you want to do your PhD, there are so many possibilities outside. It is a fascinating topic. AI is still in its early phase, and there's so much to discover. So if you want to start with AI, believe me, you do not have to have the money to pay here $10,000 per month here for cloud infrastructures. Just use your creativity. Be amazed what you find out. Listen here to others. Try to find a solution using your intellect, your brain, and you will see it can be amazing. I hope it was informative. It was great that you listened to it, that you watched this video, and it would be great to see you in my next one.